Okay, so in today's video, we are going to start digging into physics for the very first time this year. Okay, so far we've talked about what's science, what is physics, right? What are we doing here every day? What are we going to learn? Okay. Well, today we're going to dig into our first unit. Our first unit is titled Kinematics and Motion in One Dimension. Okay, so we're going to be talking about how objects move uh, and how to quantify that. Okay, through kinematics. We'll discuss those terms later. You know, as we continue this lesson, and all those words will make sense. But first, let's talk about position and displacement. Okay, that's what this is all going to be about. Before we start doing any kind of calculations, any math, we're going to talk about position and displacement because a good understanding of this is going to help us better conceptualize, the kinematics when we dig into it a little more. Okay, so your objectives. You'll be able to explain the difference between scalar and a vector quantity. You'll be able to explain the difference between total distance traveled and displacement. You'll determine displacement of an object based on a position versus time graph. You'll describe in words the movement of an object based on a position versus time. Okay. A position versus time graph. Okay, that's what we're going to do for this lesson. Now, this lesson is probably going to take a couple of days, so just be prepared for that. Prepare for multiple videos over position and displacement. Okay, so what we're trying to do here is establish a good foundation in kinematics. Okay. Okay, so motion. Motion is what we're going to talk about first. Motion, by definition, is the phenomenon which an object. Sorry about that. Is a phenomenon in which an object changes its position over time. Okay, in which an object changes its position over time. Motion is mathematically described in terms of displacement, distance, velocity, acceleration, speed, and time. The motion of a body is observed by attaching a frame of reference to an observer and measuring the change position of the body relative to that frame with change in time. Okay, so let's talk about this term, frame of reference. Okay, frame of reference. I'm so sorry. There we go. I have some issues here. Okay, frame of reference. What does that mean? What does that mean? Y'all think about that for a minute. So when you see a moving object, let's say for example, a ball rolling across the floor. Okay, we'll use a ball rolling across the floor. How fast is that ball moving? Which direction is it moving? Is it moving away from you or towards you? Right? And how we describe the motion of that ball depend on where you're at. For example, there's two people on either side of a classroom. The guy in the front of the room rolls the ball towards the back. Now, from the front of the room, or from the perspective of the guy that rolled it, you would say that it's rolling across the floor away from him, right? But what about the guy in the back of the room? He's going to say, oh, no, it's not. That ball is rolling towards me in a positive direction. Okay? That means motion is relative. And how we describe it and how we quantify it depends on our frame of reference. Let's watch this video here at the bottom, and we'll dig into this a little deeper, and you'll know more about what it means. so we can pull it up real fast. No, I don't want YouTube ads.
Professor Dave here. Let's talk about relative motion. He knows a lot about the science of Professor Dave explains. By now, we understand that physics is concerned with the motion of objects and the quantitative analysis of that motion. But this can be tricky business if you really think about the fact that everything is in constant motion. When we say that a car is moving at 100 kilometers per hour on the freeway, we are ignoring the fact that the surface of the Earth is rotating around the center at about 1,700 kilometers per hour at the equator. Earth is also moving around the sun at around 30 kilometers per second. The entire solar system moves around the galactic center at 20 kilometers per second, and the Milky Way galaxy is moving through the universe at about 230 kilometers a second. So it's not completely wrong to say that the car is actually moving with this incredible speed as well, meaning that in a certain context, there's practically no difference between flying in a plane and sitting still in terms of absolute velocity. But that's why we tend to discuss relative motion. We don't notice the movement of the Earth and the sun and the galaxy in our everyday lives. To us, the Earth seems to sit still, and a few dozen kilometers an hour may be insignificant in the grand scheme of the universe, but it's a big deal to the cop with a radar gun ready to pull you over. So we often discuss motion that is relative to the surface of the Earth. When we do this, we are assigning something called an inertial reference frame. This is the object or person or location that we pretend is completely still, and we assess the motion of other objects relative to this inertial reference frame. For example, if we treat the Earth as an inertial reference frame and we ignore its rotation and movement through space, it becomes meaningful to say that this car is moving directly north at 100 kilometers per hour relative to the ground. But if we are inside the car moving with constant velocity, it seems as though we are not moving, but rather that the surroundings are rushing past us at 100 kilometers per hour. The car has become the inertial reference frame that is standing still, and everything is in motion around us. It may seem strange to pretend that the car isn't moving, but remember, it's just as incorrect to pretend that the Earth isn't moving. So it really is all relative. Imagine you are sitting in a moving train. You toss a ball into the air and catch it. To you, the ball went straight up and down. But to an observer on the ground, the ball followed a parabolic path as the train went past. This is because when the ball leaves your hand, it still has all of the forward velocity that the train does. But if you are inside the inertial reference frame of the train is not moving at all. It is the surroundings that are moving. So the ball no longer has any horizontal velocity, only the vertical velocity you impart to it by moving your arm to throw the ball. Assigning frames of reference and understanding what they mean for the motion of objects is a big part of physics. And although some aspects of this kind of thinking seem obvious, they were not always well understood. Galileo was the first to rigorously describe relative motion after doing experiments in a moving ship. He found that if he dropped a ball while the ship was moving with constant velocity, it fell straight down, just like it did when the ship was stationary in the port. He then contemplated how a fish nearby would view the motion, with the ball moving forward as it falls, and how this differs from his own experience. He used these experiments to prove that velocity measurements depend on which reference frame you adopt, and he published his findings in a book called Dialogues Concerning the Two Chief Worlds world systems in 1632. These ideas were extended to describe the motion of the Earth around the Sun instead of the other way around, by proving that the Earth could be moving even if we don't feel it. This got Galileo and other scientists into hot water with the Catholic Church. But humanity eventually caught up to his revolutionary thinking. We refer to this portion of his work as Galilean relativity, and these concepts will be built upon to enter very strange territory when we cover Einstein's special relativity in the modern physics course. But for right now, we won't go flying through space. We have much more work to do on Earth, which, despite its rotation and motion, is actually quite a good approximation of an inertial reference frame, one that will be used frequently throughout our study of physics. With each topic we go through, whenever we examine an object's velocity, just remember, it's all relative.
Okay, so as you saw in the video, hopefully you paid good attention to that. If not, go back, rewatch it. And very well described motion and how it's relative to a reference point. Okay, very important concept. Okay, then, I touched on this earlier, but we can describe an object as moving away or towards something. Okay, depending on your reference point, there is a certain direction convention. Okay, that direction convention is going to be, we're going to use it in the terms of positive and negative. Okay, so let's look at the positive convention. Okay, so typically, you can kind of think of it as a coordinate plane. Okay, but if an object is moving upwards, we like to say that it's moving in the positive direction. Now, this isn't always the case, but I like us to all be on the same page, and you can reverse these if you like, but to keep it simple, if it's moving upwards, we're going to call that direction convention positive. For instance, you're standing on the ground, you throw a ball in the air, it's moving up. It's in the positive direction. We also say that anything moving to the right of your reference point is positive. And also anything that turns to the right, okay, turns in a clockwise motion. That's the positive direction. That's what we typically call positive, okay? That's a typical convention. When you're describing things moving to the right, think of you're standing on the highway and the car goes from your left to your right side and continues that direction. That would be positive. And I like to think of the rotation as a clock, right? A clock moves clockwise in the positive direction. If it was to totally start going the other way, we would say it's moving in the negative direction. So as you could probably predict, the direction convention for negative is are the counters of the positive side, okay? Like down and left, we typically say is negative, and in the counterclockwise direction, we also say it's negative for direction convention. So we're going to keep it short and simple today. I just want y'all to understand the definition of motion and what motion is, and know that motion is relative, and also that an object in motion has a certain direction, and that direction can be either positive or negative depending on the reference point. And we'll get more into this later. Starting tomorrow and Thursday, we'll go into vectors, scalars, kinematics, and distance and displacement. We'll dig more into this, but I just kind of want y'all to ease into it. Be sure, for the purposes of tomorrow's lesson, this is important, guys, you go back through and sign up for CK12. Okay? You need to do it. There's no ifs, ands, or buts about it. Sign up for CK12. That way I can deliver course content to you guys. If you're not signed up by tomorrow, August the 20th, then you're not going to be able to do the assignment, and therefore you're going to not get a very good grade.